talked about a few weeks ago. Then I got kind of carried away. We're going to talk about those tonight. So they are discrete distributions. And we're going to talk about 4 of them tonight. 4 of them tonight. In the video this week, there will be a couple other ones I'll mention. And there will be an extra assignment that I put up. I think I have to put up when I get home, because I don't think I have my drive with me. I just realized I don't think I posted it yet. It's a worksheet with a bunch of problems on it, and there'll be a variety of them. I think the key on this one is not to do homework from the book on this section, because when you look, well, there's going to be a few problems in the book. But I want them to be mixed up on a page, and you'll be able to pick this one out versus this one versus this one versus that one. Okay? If they're all on the page that says binomial, it's hard to screw that up. Okay? If they're just, here's an example, is this binomial, is it multinomial, is it this, is it that, what is this kind of event? So a couple that we've talked about before is multinomial, or not multi, I'm sorry, binomial. Let's start with binomial. We talked about this before, okay? Give me something that is binomial in nature. Derek, there's a lot of them.
What?
Give me something that is binomial in nature.
Anything with 2 options.
2 options, win or lose. Oh, I love it. Make it or don't make it. Well, there you go, sure. So, the classic example, just to kind of get a vision in your mind, whatever. Hey, I'm shooting that's a weird shaped basketball. There it is, cool, whatever. Yay, you're shooting hoops. Good for you, nice. Awesome, almost forgot what the basket looked like. Now, if you are I don't know, let's say you're a 40% of the time you make baskets. Right? You shoot this ball, it goes in 40% of the time. It's kind of sad, but whatever. Okay, so you shoot the ball, you have a 40% chance of making it. Okay, how did I get that data? From consistent observations over the years. Yes, I've been shooting these baskets for years, and consistently I make 4 out of every 10 shots I make. Okay. How many times have you done it? Exactly 10 times? No, I probably shot thousands of baskets over the years, yes? And of those thousands of times, about 40% of them have gone in the basket, okay? By the way, that's often how we do actual probability in real life. It's not about things like, oh, I know it's exactly 1/6 like on a dice, right? Or it's exactly 1/2 like on a coin. It isn't always that way. A lot of times you're gonna have data that you've collected over the years, and this is what you would expect to happen. As an aside, this is how you deal with people too, right? It's the first time you meet someone, you're like, oh, I'm going to go in. I'm not going to have any preconceived notions. And isn't this swell? And then you meet the person. By the way, you often judge them out the first time you meet them. Good for you. And then the second time, they either reinforce that first assumption or they make it better or whatever. But over time, you're not surprised by what that person does, because you've dealt with them in a situation a million times. And you know exactly what's going to happen, yes? And you know exactly what's going to happen when you have to deal with them, right? I'll never forget a few years ago, I had to go deal with my boss, who is no longer my boss. I don't miss her at all. But, did you say what?
The old one?
Yeah, the old one. Yes. I had to go meet with her, and I knew it was going to end badly. Oh, I knew it was going to go bad, because it always did. And so I walk out there and I start to say something to her, and she just stops me. And like makes this statement that is completely 100% opposite of what she normally would do. And I sit there with my mouth laying on the ground going, and then she walked away, and I'm like, looked at the boss, the other boss, I'm like, what just happened? And he goes, well, I told her to leave you alone this year. I'm like, oh, okay, well, you should give me a warning, because I about had a heart attack, okay? That is not what I expected from her. Over the years of collecting data on her, I was expecting this thing to go sideways. It would be horrible, just like all the other ones, and it wasn't, and it kind of weirded me out, to be honest with you, okay? Now let's think about this for a minute. This poor guy here, he's going to shoot some baskets. He's going to shoot 20 times. He's going to shoot at the basket 20 times. Shoot the ball 20 times. He has decided ahead of time, I am going to shoot 20 times, period, then I'm going to stop, okay? Here's a question. How many would you expect him to make?
50.
What?
I say 50,
15 and
Wait, it's 40 of it.
Is it 40% of the time he makes them?
So 8.
So 8. I would expect him to make 8 shots, yes? And I know this because why? Well, yeah, that 20% times, or 40% times 20 is 8. I would expect him to make right? I would expect him to make 8 baskets, right? It's going to go in a basket 8 times. That's what I expect him to happen. I'm not shocked if he hits 7. I'm not shocked if he hits 9, probably, yes. I'd be weirded out if he hit 15, yes? That's way, way weird. I'd also be shocked if he only made 2, right? I'm expecting somewhere in that 8 range. Okay, now what does that sound like? That sounds like expected value. Or, wait for it, if you prefer, what's another name for that? It's kind of like a long-term average. Okay? But expected value, we've studied this. The expected value, you recall, is the sum of the xi's times their probabilities, yes? That's something that we've talked about, right? We've said that there's all these different possible outcomes. But in the case of a binomial, there are 2 parameters, n, which is the number of times we play, often referred to as the number of trials. In this case, the guy's going to shoot 20 times. He's playing the game 20 times, okay? And then he's stopping. It could be rolling the dice, it could be flipping a coin, it could be having children, it could be whatever there is, as long as it is binomial. I know what you're thinking, a dice is not binomial. Sure it is. It's a 1 or it's not a 1. You with me? Now, could it be something else? Could it be 1, 2, 3, 4, 5, 6? It could be, but I could look at it as binomial. I have to get a 1. You must, come on, Daddy needs new shoes. Give me a 1. Well, I know there's either a 1 or it's not a 1, yes? And by the way, it's not likely to be a 1, is it? No, it's not likely. It could happen, but it's not likely. But, listen, this is important. So, there's 2 parameters. There's n, which is the number of trials, or the number of times you play, and p, which is the probability of success. And so the expected value on a binomial is simply n times p. That's a special case. It only works for binomial. Right? Now, if you're weird, Chad, you could find all the possible outcomes. He shoots the ball 20 times. You can make none, or you can make 1, or 2, or 3, or 4, or 5, or 6, or 7, or 8, or 9, or 10, or 11, or 12, or 13, 14, 15, 16, 17, 18, 19, or 20. That's a lot of work. And then you could take each of the x's times their probabilities, and you would sum them up, and you'd still get 8 when you're all said and done. Because it is simply always going to be n times the probability, times p. That's it. It's easy money. Yes? Now, that's kind of exciting. Now, you're like, is there a variance formula too? Yeah, it turns out there is. For a binomial, the variance is simply equal to n times p times this guy, which is q. You're like, what's q? Well, if p is the probability of success, what's q?
Probability of failure.
Oh my word, did you just say the F word? Yeah, probability of failure. You're right. Or, if you're weird, and some books are, it's just 1 minus p, right? So if there's a 40% chance of making it, there's a 60% chance of missing it, yes? 30% chance of rain today, 70% chance of not rain today. Okay, it's the only 2 options there are because it's binomial. Right? Nice. Now, a couple other things to talk about binomial. So these are all facts, and I think when you go back up here, it makes perfect sense that you're going to shoot the ball 20 times, and you make 40% of them. That I expect to make 8 of them. That seems pretty easily done. Okay, and again, I think that's the easiest way to picture that, and so to me, that's kind of how I always start these guys off. But here's my question, or my statement to this: a binomial distribution. There are 2 mutually exclusive outcomes. That is if you prefer win-lose. You know, live or die. I don't know, dead or alive. Boy or girl. Whatever there happens to be, okay? There's just two outcomes. Okay? And this is important. The probability, so we're going to have a set number of trials. That is, I'm going to play a certain number of times, and I know that before I begin. And the second thing, or the last thing is this: the probability of success must remain constant. What's another way of saying that this shot is not affected by the previous shot? What's another way of saying that? They're independent. So there's n independent trials. Are you with me? That's what we're saying. There's n independent trials where there are two mutually exclusive outcomes. That's another way of saying this. Okay? In other words, now remember, in real life, sometimes you have to kind of fake it a little bit. If you're shooting baskets in the backyard, you probably aren't going to put a lot of pressure on yourself. So whether you make it or you miss it, nobody cares. If this is a game situation and you make the first shot or you miss the first shot and the game is on the line, is the probability going to stay the same? No, not at all. And so there are some times when what seemingly looks like binomial can actually be affected, yes? So if I miss that previous shot, now the pressure's on, and then my probability goes up or down based on that, okay? So we have to make sure those assumptions are met. Sometimes we have to fake it just a skosh, okay? We have to pretend, but it kind of depends on the situation. We'll point some of those out as we get to them, okay? My brother, when he had, well, okay, I had to start with by saying this, is that, you know, I'm very superstitious, which sounds weird. I'm not very, kind of superstitious about things. Like the rational side of me says, come on, stupid, that doesn't matter. But the other side of me goes, now I'm weirded out. This is going to be weird. So my brother had a girl, and then a girl, and then a girl. In that order, girl, girl, girl. My next thought was he's going to have another girl. I know he is. And by the way, I wasn't shocked that he had girls, because that's what my mom wanted to have was girls, and she got stuck with two boys. And then, of course, he's the favorite, so of course he's going to have the girls. All right? And so in my mind, I'm like playing those games out. But in reality, he's just as likely to have a boy as he is to have a girl each time, yes? And, oh, he had 3 girls in a row. That means the next one has to be a boy. Yeah, keep telling yourself that. There's a lot of people that have like 5 girls, and then they finally say, we'll stop, I guess, because I guess we're not getting our boy, or the other way around, yes? But whatever. What's interesting about that, I think I told you this, he had 3 girls and he had 5 boys in a row, all right? Which seems weird, but it's just as likely as anything else to happen, because each time it's exactly 50-50. There's no, well, more or less 50-50. It's not affected by anything, okay? Oh, you had 3 girls in a row, the next one's got to be this. No, it doesn't. Keep telling yourself that. By the way, that's also true for gambling. That's how gamblers got into a lot of problems, because they say things like this themselves. Okay, the next hand, or the next roll of the dice, or the next spin of the wheel has to go my way. No, it doesn't. No, it doesn't. It's just as likely to go against you this time as it was last time. And by the way, just the same works the other way. Like, oh, I'm hot. I'm going to keep winning. Yeah, no, you're not. No, you're not. It's going to catch up to you eventually. Okay? Each time is completely independent. That's something we have to hang our hats on when we do these guys. Okay? So keep that in mind as we're doing them. It's kind of fun. So let's do this thing. Suppose we write this down. If I ask you, we're going to shoot 20 shots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 20 shots. He could do this. He could make one, and then, I don't know. Well, that's weird. I'm not going to do make and miss. Let's do basket, and then a miss, and then a miss, and then a basket, and a basket, and a miss, and a miss, and a miss, and a miss, and a basket, and a miss, and a basket. 1, 2, 3, 4, 5. Whatever, right? So he hit like 7 baskets here, yes? I think I counted 7. I don't really pay attention to myself, okay? The probability of this happening would be what? Well, it'd be a 40% here, and then times a 60%, times a 60% times a 40. I have no time for this. This is stupid. What is a better way of writing this? Well, I see making a basket 1, 2, 3, 4, 5, 6, 7 times, yes? And the rest of them, oops, sorry, wrong spot. 60%, there you go. The rest of them would be misses, yes? But here's my question. Is this the only way you can make 7 baskets? No, there's a lot of different ways, yes? In my mind, there are 20 times he shot the ball, and I'm choosing 7 of them to be made baskets. Okay? What that means is those B's can be sorted out amongst those 20 spots, 20 choose 7 different ways. Okay? This right here is the probability that the guy makes 7 baskets. Right there is equal to this thing right here. Okay? That is what we call the binomial distribution. If you look at it, it is this. It is n choose x times p to the x times q to the n minus x. So, in our calculators or in Excel or however you want to do it, I'm going to run through about 8 different ways. You pick the one that makes you the happiest, and then it'll make me the happiest too. I'll do Excel first, I guess. In Excel, it's equals binom dot dist, the binom dist. Whatever, that guy right there. Okay? And then it says it wants the number of successes. Okay, well I was talking about making 7 baskets, so that's cool. Then it wants the number of trials. He shot the ball 20 times, yes? So 20. And it wants the probability of success, so 0.4. And then the next one, cumulative. What this thing is, right, we're looking at right here, is both a PDF and a CDF at the same time. So if you put a 1 in there, you made yourself a CDF. Okay? If I put a 1 in there, it's the probability that x is less than or equal to 7. Okay? If I put a 0 in there, it's the probability of exactly 7 baskets. Okay? So if I put a comma 0, this means the probability of exactly 7 baskets. If I do that, it's a 16.5% chance that he makes exactly 7 baskets. This right here is the probability that x is equal to 7 exactly. Okay? That's when that cumulative piece is exactly 0. Okay?
So it was the number needed, like number to make it, the total number, the...
Well, so it's x, then n, then p, and then you decide whether you want cumulative or not cumulative. Okay? And you're like, oh, that's cool, Jay. So what if I wanted a CDF? What if I wanted this probability? What if I wanted probability that x is less than or equal to 7? Well, then I want a PDF, yes? Or CDF, rather, right? So the CDF is exactly like it was above, except I'm going to throw in the 1. Just like that, yes? This will be a CDF. And that comes out to be, basically 42% chance that he makes no more than 7 baskets, yes? Nice. Right? Oh, just for fun, while I'm here, because I like to do this, what's the probability that he makes more than 7 baskets? Now, there is no formula for this in the computer. You have to just think about it a little bit. How would you find that guy? 1 minus the other bit, yes? Nice. Nothing to it. Okay? So it'd be like, I don't know, 58% or something, yes? 58.5, give or take. Got to play? So that's that. If you want your TI calculators, I can do those too, because I speak computer sometimes. Virtual TI. There we go. Open up. All right, so on the TI 89, if you go to apps and you're looking for stats list editor, mine looks a little different than yours. If you go under F5 for distributions, F5, and then you scroll down a ways, you will find binomial, both PDF and CDF. So binomial PDF, give it to me. Oh shoot, darn it. Just a minute. Binomial PDF. And so we're going to play 20 times. Probability of success is 0.4. And then I want to win 7 times. So there's our 16.5%, just like before. Nothing fancy there. And then you could also do the next one down, which is the CDF. And the 89 is kind of cool because it allows you to put an upper and a lower bound in. But if you want to get the same example, like the same answer I got here in Excel, you just go from 0 to 7. If you do that as an upper and a lower bound, and you'll see that it's 41.5% again. Okay. The nice thing about this calculator is it basically, well, they're all doing integration. Okay, they're all doing integration. So, but this one allows you to change the limits of integration. So instead of going from 0 to whatever on the top end, this one allows you to change both limits of integration. There you go. You get it? So if you go here, apps, right there, and then go up here and find your stats list editor, right there. And then just F5, and binomial PDF, and 20. 0.4 and 7. That's when we did it first. So there's that. Or if you want to do a CDF, and then traditionally I like to go from 0 up to the value. Okay, this one allows you to change both limits of integration if you want to. There you go. Okay. Anybody have 84, 83? You want to see that one? Nice, I don't have to do that one. Yay. One less thing to do. Okay? But if you, oh, you have an 84, you want to see that? Or you want to do Excel? You want to see 84? I don't care, let's do it. Let's do it. Why not? I just want to show off, impress the people. Give it, come on. Come on, where's my thing? I don't have a cursor anymore. Nope, there it goes, okay. Boom, 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 boom. All right, cool. So in this guy, you do second, and then the bars right here, distribution. And then you go to, do you go down a ways? Does yours have a drop-down menu? Or does it look like this?
It looks bad.
Like this? Okay, so what you, so you do 20. So 20, that's it's N, comma P, comma X. 7 in this case. Well, I didn't get a comma, just a minute. Comma 7. Okay?
Okay. And does look a little bit different.
So you have a drop down.
I guess.
Cool. Yeah. So then 20.4, 7.
Oh, okay.
And then paste. And then it looks just like mine. And then hit enter. And there's your 16.5. And the CDF is exactly the same. Second bars. Binomial CDF. And it'd be 20, comma, 0.4, comma, 7. And there's your 41.5% again. Okay? So regardless of how it's doing it, that's the only thing. 89 is kind of cool because you can go, you could find greater than 7 pretty easily, or let's say if you go from 8 to 20. I don't like doing that because every other CDF program out there does less than or equal to by definition. So I just get in the habit of finding less than or equal to, and then 1 minus that to find the above part. That's just the easy way to do it. Because what's going to happen is this thing only, the 83s, 84s, 89s, they only do certain They only do certain distributions. So then I'm going to have to go find out a different way to do it. And then the other Excel, Minitab, S+, all those, they all just stick with the traditional definition of the CDF. So you're going to want to get in the habit of doing it that way. All right. So that's kind of fun. It's kind of neat. Let's see here. Let's do this. Cool. Let's see. So you, I don't know. Let's see here. Let's do, I don't know, 5% of all, I don't know, these resistors from this company are defective. Okay, whatever. So let's say there's just giant shipment of them, and you select, from this shipment, we're going to select 40 of them. All right, so right off the bat, how many would you expect to be bad? So you select 40 to test to see if they're good or bad. 2%, or typically 5% are defective. So how many would you expect to be defective out of 40? 2. I would expect 2, yes? Because of this, the expected value is just 40 times 0.05, yes? I would expect 2. It would be weird if I got 4 or 5 or 6 defective. That'd be really weird. It'd be impossible, basically, to get 30 defective out of 40. Right? It'd be like off the charts, impossible, cannot happen, yes? Now, in theory, could it happen? Of course, it could happen. It's not going to happen. Okay? Am I right? Am I right? Now, by the way, this is why we do quality control. You take a sample out and you test them, and out of 40, you would expect 2 to be bad, but you got 12 to be bad. Whoa! Shut the thing down. We're making bad resistors. Something's happening, yes? Because out of a sample of 40, I expected 2 to be bad, all right? It would be beyond impossible, basically, for us to get 12 bad if nothing has changed, yes? But something is obviously broken, all right? Something's not right. We got some bad, whatever it is we're making, silicone, yada yada, something, something, throw out some fancy words. Something is wrong, okay? So shut that sucker down. Now, if I did this, what is the probability that I get 3 defective? 3 defective resistors. Okay, let's find that out. Okay, now if you were doing it the hard way by hand, it would be 40, choose 3, times 0.05 to the 3, times the rest of it to the 37 power, right? Because that's the rest of them. I don't need you to do it that way. What I need you to do is find the answer. So for this guy, I would go equals binomial dot dist. And we want 3, by the way, successes. You with me? It's successes. Having a defective resistor, I don't think really feels like success to me. Neither does dying. And yet, from an insurance company standpoint, or from your standpoint, either case, like for life insurance, nothing happens until you kick the bucket. Okay? Nothing happens until you die. So if you take out a life insurance policy, you are betting that you will die. That's what you're betting. So for you to win, be successful, you have to kick the bucket, which is less than bueno. Okay? But it's one of the bets you want to lose. Okay? So it's 3, comma, we played the game 40 times, and the probability of success is 0.05. And if I just put in a 0, this is the exact probability that I get exactly 3 defective resistors out of 40. Okay? Exactly 3. Oops. Oh, you leave me alone. About 18% chance that this happens, yes? Which is not horrible, okay, of a chance of happening. Now, if I said to you, what is the probability that I would get more than 3 defective, what would you do? Well, I would rewrite that probably like this because it makes me happier to see it like this, yes? How would you find that answer? There is no function that finds this. So what would you do? What is the less than?
Less than 4. And then
Oh, okay. But good. No, I love this. This is amazing. Less than 4, you cannot have 3.75 effective resistors, yes? Because this is a discrete distribution. So less than 4 is another way of saying less than or equal to 3. Am I right? There is nothing between 3 and 4 in the case of defective resistors. Is it 3 or is it 4? I don't know. Pick one, yes? You cannot be in between somewhere. So another way to write this is this. And I know that that's equal to 100%, yes? I shouldn't say this is not equals, but this is what I want to find. What I want to find is I want to find this guy. I don't know how to find him. But this right here is the very definition of a CDF, yes? So I will find that, subtract it to the other side, and be done with the thing. Now, if you go into your Excel, which I just had up, the nice thing I like about Excel the most is, boom, I just made it a CDF, yes? That's all I have to do to change it from being a PDF to a CDF in Excel. So when I do that, I get 86%. So I just do 1 minus that. So there's about a 13% chance, 13.8% chance that I will get more than 3 defective resistors. By the way, most of that is the probability of getting 4 defective resistors. You with me? Most of that 13% will be the chances that I get 4 defective resistors. There's very little chance I get 5. There's almost no chance I get 6, and so on and so on and so on. In fact, this is what I kind of like to do sometimes. See if I can do this without screwing it up. One to 40. That's nice. And what you can do, and I think it's kind of neat, is this. You can go equals, binomial. This is for a nice teaching perspective, I think. I want to get that many wins out of 40, comma 0.05, comma 0. So if you look at that, there's a 27% chance. Oh, I missed 0. Darn it. Never fear. I'll just add a line. Try that again. Oh, fart. Yay. So, if you take 40 resistors out, there's a 13% chance that none of them have a defect out of 40. You with me? There's a 27% chance that you get 1 out of 40 bad ones. There is a 27.7% chance that you get 2 defectives. There's an 18% chance you get 3, 9%, 3, and so on and so on and so on. From here all the way to 40 adds up to, what did I say a minute ago? What did I say a minute ago? I wrote it down somewhere. Where did I put it? It's over here in column A. Get over there. Go to column A. There's a 13% chance from here all the way down. That only adds up to 13%. Okay? Because I know this because from here back was 86%. From here down then has to be the rest of the 13.8%. Notice that this guy right here is more than, what, 2/3 of it, yes? Of that 13%. This next one is most of it. And if you go down here a ways, pretty soon the computer just says, oh, screw it, it's not going to happen. You see this? E minus 13, E minus 20, E minus 40. Oh, props to Betsy. Look at that. She never quit on us this time. Are you with me? Didn't ever quit. Most times she just says, oh, screw you. Take E to the minus 50, it's a 0. It ain't going to happen. Okay? But props to Betsy, she didn't give up on us. Okay? But listen, for all intents and purposes, 49 zeros and then a 9, or well, wherever I left off, 49 zeros and then a 6, I guess. It's not going to happen. That is not going to happen. Again, it's not going to happen unless what? Unless something has changed. Are you with me? When we go into this thing, we assume, based on long-term averages, that out of 40, we expect 2 bad ones, yes? Or in other words, we expected 5% to be bad. If that's true, it should expect that forever and ever and ever, unless something has changed. By the way, that is the very basis of what we test on in statistics. When we do tests like this, we know that this is what's supposed to happen. I'm not shocked if I take out a sample of 40. I'm not shocked if I find 4 defectives. I'm not happy about it, but it's 9% chance of happening. It could happen. I'm not shocked if I get 1 out of 40 bad ones. That doesn't shock me. It's legitimate. It could happen. But I'm talking about if I get 7 or 8 defective ones, ooh, the chances that happen, basically none. If nothing has happened. You with me? Because that is what we base everything on. We go in assuming something is true. Did it stay that way? I don't know. That's the trick. Now, it's at this juncture I'd like to continue do something else that kind of relates to this because it just kind of fits. So I have this one card trick that I know. Perfectly normal deck of cards right here. Okay, pick a card, any card. Doesn't matter if I see it or not, that's not the bit. Matter of fact, we're going to write them down. Jeff, you write this down for me. It's a 6 of spades. 6 of spades, right on. I'm just going to shuffle behind your computer. I suck at shuffling. But I wish I was good at shuffling. It would really make this bit a little better. I'm not hiding, I'm just doing it behind the computer so I don't spew them all over the table and then people laugh at me. It's hurtful. Okay. Other than that, I mean, if I could do the whole bridge thing, it would really sell the bit. But I don't know. All right, pick another one. Any card, any card. But I saw on Reddit you must shuffle 87 times. Oh, for God's sake, right here. 7 of clubs. All right, now. By the way, it doesn't matter where I put it in the deck. That's not important at all. Now, so far we've got what?
6 of spades.
That's it. We got a spade and a club so far, whatever. Now, wait, is anybody panicking that I have not seen a king yet?
Yes.
You are?
Yes.
Okay, yes, she is. So I know she's pulling my leg. It's kind of weirding me out. I'm not shocked that I've not seen a king. Why? What's the probability that I see a king? Well, it's 4 out of 52, yes? Which is 1 out of 13, which is give or take about 7% chance of happening. So I'm not going to cry about that I haven't seen one yet, because, well, it's about a 7% chance every time of that happening. It's probably not very likely to happen, yes? I'm not panicking about this yet. What did you get?
3 clubs.
3 clubs. 3 clubs. All right, now, we'll keep going here. What we're looking for, don't be staring at my, don't be staring. You might see the trick. Now,
Is it a half deck?
is it a half? No, it's a full 52 deck of cards. We could play 52 pickup here in a minute, but that would kind of ruin the whole thing. What's that? Yeah, it would. Nope, full deck of cards is here. Full deck.
Playing with more than I got.
Ooh.
Jack of clubs.
Jack of clubs. Now, did anybody notice anything so far? Oh, I'm sorry. I did want it back.
Put all the club or all the down.
What did you say?
What?
What did you say again? Say again.
She put all the black color out.
She's only pulled black cards out so far.
Mm-hmm.
Now, is that shocking to me?
No, I mean you gotta.
Well, let's find out.
And, like,
How many cards have we taken out thus far? Don't touch. Don't touch. How many have we taken out so far? Is that 5?
4.
4. Wait a minute. What's the probability that get 1 black card? 50%, yes? Oops, well, let me write this down. I got a little carried away. 1 black card is equal to 0.5, yes? Right. And what's probably I get 2 blacks in a row?
Well, we're putting them back. So
We are.
1.5. Or not 1.5, but
0.25, yes? 50 times 50, right? 25%. And then, of course, 3 blacks would be 12 and a half, right? And then 4 in a row would be 6 1/4. 0.625. There it is. Yes. And then I've done 4 cards. You said or 5? 4. Now at this point, there's a 6 1/4% chance that I would see all black cards in a row. Now is that mildly out of the ordinary? It's mildly out of the ordinary. It is about the probability that you see a lady that's about 5'10" or taller. Wait, I saw a couple of those today, Jay. I don't feel like that's ridiculously out of the ordinary. It's a little large, but it's not that ridiculous. Let's go again, shall we? I'm going to shuffle them again. Did you cheat? Look at my card.
No.
Okay. No, I was going to, but you stopped me.
I was.
Now, the first time I saw this trick, a friend of mine did it. She taught math for years, and she did it at a conference one time. And it was a conference. Her talk was the problem with probability in middle school. The probability in middle school is teachers don't get probability. And it was pretty obvious from the teacher she was talking to, no clue.
Two of spades.
Two of spades.
Another black one.
Ooh, another black one. The probability at 5 blacks is what?
Have that like 5.
0.03125. 3% chance that happens, yes? When are you gonna just drop the old I'm calling bologna sauce on this thing?
Right about now.
Right about now. Right? Maybe 2 cards
I
ago.
say another 2 more.
You say 2 more.
Another 2, yeah, at least another.
So 2 more. So you're saying no, I'm gonna go 1.5% and then 0.75%. It feels weird, but okay. Now, the first time she did this, after the second black card in a row, she went, they're all black, they're all black. And she like mocked these people so much so that no one said a word because they felt so embarrassed. Then she drew 8 black cards in a row before someone said, well, yeah, maybe that's weird.
I mean,
No,
you
that-
put all the black card in there.
No, I don't. No, listen, here's my point. Here's my point. Based on our assumption is that this is 50-50, yes? What we've seen is odd based on our assumption, yes? We went in thinking that this should be 50-50. But what I witnessed from my sample right here, there's about a 3% chance of happening. That feels weird to me. So something is wrong. Either my assumption is wrong, or I witnessed a rare event. Now, what are you going to bet on?
Probably the
Second
former.
event.
Yeah, well, I'm certainly going to bet on the rare event because that happens every day. No, I am wrong every day in my assumptions, aren't you? That's right. So, can we say that they're all black?
Yeah.
No. We cannot say they're all black. This is what we can say. We can say with pretty good certainty that they are not 50-50. Are you with me? I cannot say that they're all black. I can just say that I'm very confident that they're not 50 black, 50 red. Okay? In other words, that's how statistics always works. I cannot tell you what it is, but I can tell you it's not that. Okay? And so, yes, the trick is, yes, it happens to be 2 black decks put together. But if there had been 1 red card right here, would I have been likely to pull him out?
If you see the card.
Well, no, I mean, would she have been likely to pull it out if she can't see what it's there?
No.
No. Would I have been just about as likely to get what I saw here if I'd have had 1 black card? In other words, I'd have been just about as likely to get all blacks, even if there's only 1 or 2 red cards, yes? So the idea here behind this little trick is that this is how we always go about statistics. We always go, hey, either in this case we assume they're 50-50, okay? In the case of this, we knew from past experience that 5% of all these resistors are bad, okay? Well, if nothing's changed, that should still happen again and again and again. However, for quality control purposes, I take them off the line every day and I test them. And if all of a sudden I pull out 40 of them and I get 10 bad ones, dude, either you witness something very rare or more likely something's wrong. Yes, we assumed that they're still 5% defective. In fact, something's changed. The machine is broken, something's wrong. We're getting some bad silicon, blah, blah, something, something. Something is not like it should be, and we should probably go fix that. Okay? That is what we mean in statistics when we talk about what's called hypothesis testing. We'll talk about that much more later on. But what I want you to get in the habit of saying is this, is that looking at that data I gave you over here, look at this data table, you can see, based on this, hey, these first 3 or 4 are fairly likely to happen, yes? That's fairly likely. These are not going to happen. They're really rare chance of those happening. However, if that were to happen when you take a sample, that doesn't mean something really rare happened. In fact, what's more likely to happen is that something has changed. Something has changed behind the scenes. And that's what we need to go look at. Okay? So binomial, 2 outcomes. They are independent events, each time I play, and I play a set number of times every single time. Now, I like binomial. It's one of my favorites. It's pretty kind of neat, kind of easy to do. It's kind of fun. There's several others that are very closely related to them. One of them is the multinomial. What does that sound like to you? What's that? More than two outcomes, but they'll be mutually exclusive, yes? There's no overlap, in other words, yes? There's no, well, I'm kind of this and kind of that, right? So instead of being just, live or die, it's going to be like this. I get a 1 on a dice, or 2, or 3, or 4, or 5, or 6, yes? There are multiple outcomes. The probability of success will remain constant. In other words, they're not going to change. Every time I roll the dice, it's 1/6 for all the sides. Okay? Those are the key things. So we're going to have n independent trials again. Remember, independence is another fancy way of saying the probability of success remains constant. And you're going to have not one p this time, but multiple p's. Right? In other words, you're going to have a bunch of probabilities here. What will they all add up to? The sum of all the probabilities, I goes from 1 to k, better add up to 1. Exactly right. No, this is sweet, dude. Check this out. This is what it looks like. The formula is this. It's n factorial over x1 factorial times x2 factorial dot x sub k factorial times p1 to the x1 times p2 to the x2 dot p sub k to the xk. In other words, it looks almost exactly like the binomial distribution. Almost exactly like it. And if there were only two of them, if there was just this, if there was only two outcomes, this would be P and this would be Q, yes? And if there was X1 winners, the rest of them would be losers, yes? So in a case of two, if there's only two outcomes, this thing just simplifies down to binomial. This deal right here is the number of ways you can rearrange. Like if you're drawing M&Ms or something, like you pull an M&M out and you look at it and you throw it back in and then do it again. Because it has to be independent. I cannot pull the marble out and eat it or something. I have to put it back in the jar and draw again. It has to be independent every time. But what this is saying to me is this: if I play this game n times, what's probably I get 4 red ones and 3 blue ones and 6 yellow ones and so forth. Okay? This is what multinomial is. So let's do this one. If you roll, let's do roll a dice, something boring like rolling a dice. So you're going to roll a dice 10 times. What's the probability I get 1, 3 2s. Well, that's weird. 3 2s. 4. Quit doing that. 4 5s. So 4, 7, 8, and 2 6s. In theory, 2, 4, 6, and 3 and 9 is 10. So there's 10 of them there, yes? That makes sense? I rolled the dice 10 times. I got number 1. I got 3 2s on the dice, right? And so on, yes? So when I do this, it's going to be 10 factorial over, now I got a 1, so it's going to be 1 factorial. I have 3 2s, so 3 factorial, 4. Now you're like, wait, Jay, you skipped the 3s. I did. So I had no 3s and no 4s. And I had 4 5s. And I had 2 6s. Okay? Now if you think about this, these numbers down there, 2 plus 4 plus 0 plus 0 plus 3 plus 1, better up to 10. That's how I always check myself. Make sure that those guys add up to 10, because that's what they really are. The sum of the x's is equal to 10. Times, well, probably I get a 1 is 1/6 to the first power, 1/6 to the third power, 1/6 to the 0. I'm going to go ahead and include them all, just so that you get the picture of how it works. That makes sense? That's how the formula works. We can clean some of this up a little bit. Some of it cleans up pretty nice. Because, for instance, 0 factorial is another fancy way of saying what? It's just 1. Better not be 0, we're screwed. These are both 1s, yes? All right, 1 factorial is also 1. 3 factorial is 6. If you can do these in your head, good for you. 4 factorial is 24. 2 factorial is 2. If you can do those in your head, that makes your life that much easier, yes? And so I don't know what the answer to this problem is yet, but I feel like it is, that's bottom's like 288, I think. Might want to check my math. And then because these are all the same, it is 1/6 to the 10th power, yes? I think so, isn't that right? By the way, 10 factorial is a pretty good sized number. What does that come out to be? I don't know, pretty good size. But then remember, the answer is going to be fairly small. Is it weird that we didn't get any 3s and 4s? It kind of is. In a perfect world, out of 10, I expect 1 out of every 6 of them to be a 1, yes? That's like 1 2/3. That's a little weird, but not totally weird, right? I got multiple of some of them. I didn't get any of other ones, yes? So it's a little strange, not terribly strange. What's weird is that I got 4 5s. That's kind of weird to me. Are you with me? The not getting any of the 3s and 4s doesn't shock me a great deal. But that I got 4 5s is kind of weird. Okay? And as a result, I'm thinking Jesus feels dirty or weird to me. Well, what that's telling me is that, first of all, I'm thinking about it right, number 1. But number 2, I'm probably going to get a small probability here when I'm all done. Well, let's try it. So it's 10. And on this calculator, if you go second, math, 7. So 10 factorial divided by 288 times 1 divided by 6 to the 10. Oops, nope. Try again. Nope. Delete. Oh, I know. Hit it again, you moron. Yes, there's that answer. Or if you prefer diamond enter. No, give it to me. About 0.0002. In other words, it's not very likely to happen. You with me? It's not very likely to happen at all. But think about this. How many different ways can you get answers for 10 dice? Well, there's a lot of ways to do that. There is a lot of ways. There's only 100% to go around. Are you with me? There's only 100% to divvy out to all those possible outcomes, yes? So even the most likely one to happen has very little chance of happening. Okay? Even the most likely one, this is not the most likely, by the way, but even if I did a very likely one to happen, which is that would be like 2 of this one, 1 of this one, 2 of this one, 1 of this one, 2 of this one, 1 of that one, that'd be fairly likely to happen. Even that one wouldn't be very likely to happen. I'd get like maybe a 4% chance of it happening or something like that. And why is that? Because there's so many possible different ways it could happen and only 100% to go around. None of them are going to be very likely. Okay? So just be aware of that on this kind of problem. That's always going to be true. Okay? They're just going to have tiny, tiny, tiny little answers as a general rule. Okay? Again, if you do this and you get a number greater than 1, you screwed up. You're finding a probability, for crying out loud, right? It happens to the best of us. You're going along, I got 7. Sorry, pal, you did not get 7. Okay, you shouldn't have got 7. You're trying to find the probability. You're looking for a decimal answer here. Okay. Again, that just comes from you got a parenthesis in the wrong spot. Something weird. Go figure it out. Okay. But don't panic because literally we've all done it multiple times. Okay. Multinomial. Watch this. Listen to how I phrase this question. You're going to roll a dice. Your first thought is what? Multinomial or binomial? It feels multi, but it depends on what I say next, yes? You're going to roll a dice 15 times. That doesn't help, doesn't tell me anything. What's the probability that I get 4 6s? Multinomial or binomial? Binomial, because either I got 6 or I didn't get 6s, yes? So when you look at this, This would be, I didn't mention the 3s, the 2s, or the 1s on the dice. I only talked about 6s. So either they're 6s or they're just combined into not 6s. So it's going to be 15, choose 4 times 1/6 to the 4 times the rest of them to the 11 power, right? And of course you can do that with the binomial dist if that makes you happy. Equals binomial dist. And I wanted to get 4 wins. And I'm going to play 15 times and 1 divided by 6 and 0. Which is about 14% chance of happening. Roughly. Yes, no, maybe so. What's the matter, Terry? What's the matter? Okay. You look sad. You look like you're confused. Okay. This is why I'm not a counselor. Oh, you look like crap. No, I was happy till I came to see you. Yeah. What's your problem? Oh, well, now I'm going to make you better now. After I ruined your day. All right.
I'm not better. Get out.
There you go. Yeah, that's how I feel about it. There's a 3rd period girl tomorrow. That's what it's going to be tomorrow. As soon as she walks in the door. Oh, bye-bye! Yeah, I was so nice to her the other day. No. I got better things to do. Good day. Screw you guys. Get him. Multinomial. Fun times. Now, ooh. Let's do that one.
Run.
Hmm?
Run.
Right, let's roll 2 dice. Nice. What is the probability that I get a 6 or a 7 or an 8? Well, let's don't write it this way. I'm sorry. No, let's don't do that. It's probably that I get, if I roll 2 dice 10 times. It's probably that I get 3 6s. That's a sum of 6. 2 7s. 2 8s. And how many other dice are there? That's 7. 3 others. Okay. Multinomial or binomial? Quite clearly multi, yes? If it was bi, you would have just said, probably like a 6 or something, yes? So let's think about this. How many ways can you get a 6 on 2 dice? How many ways can that happen? Oh, for heaven's sakes. I could get a 1 and a 5 or a... Wait, hold up now. I could get a 1 and a 5 or a 5 and a 1. Are they the same? One of my friends told me years ago, try this. He goes, use different colored dice. It was the craziest thing. The kids would say 1 and 5, 5 and 1 are the same. But when you give them a red dice and a green dice, oh my God, they're different. Yeah, you're right. Why did it work? I don't know, but it does. All right. So listen, sir, you cannot have 2 white dice. Here, you have a white dice and a red dice. Oh, I get it now. Whatever, dude. So 1 and a 5, 5 and a 1. That's 2 ways, yes? 4 and a 2, 2 and a 4. Or?
3.
Oh, 3 and a 3. Can you do a 3 and a 3 the other way?
Yes.
No, because they're the same on both dice already. The reason I can do a 2 and a 4 or a 4 and a 2 is because both dice had a chance to be a 2 and then a 4 or a 4 and a 2. But a 3 and a 3, what are they both? They're both 3s, aren't they? You with me? So you can't flip them around because they're the same. So there's 5 ways to do that. Probably to get a 6 is 5 out of 36. What about a 7? How many ways can you get a 7 on 2 dice? 7. So let's start off. 1 and 6. 6 and 1. 2 and 5. 5 and 2. 4 and 3. 3 and 4. There's 6 out of 36. By the way, 7 is the most likely thing to happen on 2 dice. Now, if you're a betting man or lady, as the case may be, what's the probability of 8? Take a wild stab at it. Go ahead. Come on, you can do it. Yes! That's right. But why? Okay, 2 and 6, 6 and 2, right? 5 and 3, 3 and 5, 4 and 4, but can't be reversed, yes? It's 4 and 4, just same on both dice, yes? I'll break out the green marker and the blue marker, friend. I'll do it, all right? But you can see that if you do a 5 and a 3, or a 3 and a 5, that's different, yes? The 4 and a 4, there's no way to change that up because they both had 4s on them, yes? There it is. Now, what do the rest of them have to add up to? Well, so far that's 16 out of 36, yes? So the probability to get something else is what? Is 20 out of 36, right? But what if it was like an 11J? That fits into here, sir. 20 out of 36 is one of those. Some of those are 11s, yes? Nice. So it would look something like this: 10 factorial. And then I would have 3 factorial times 2 factorial times 2 factorial times 3 factorial, yes? 2 plus 3 plus 3 plus 2, it adds up to 5, adds up to 10 on the bottom. Right? 2, 3, 2. Not the factorial, but the 2 and the 3 and the 2 and the 2. Those, if you add them up, adds up to 10, yes? That's just a check I like to do for myself, see if I'm right, okay? Or if I'm on the right track. So 5 out of 36 to the third power. 6 out of 36 to the second power. 5 out of 36 to the second power, sorry. And the rest of them, which is 20 out of 36, to the third power, yes? And I always like to double check myself. This plus this plus this plus this adds up to 1, yes? And the top guys, the exponents, better add to 10, right? That's all of them. That's your answer, whatever that comes out to be, whatever grossness this thing is. Okay? I'll bust it out and play along. Now, this is one of these deals where I'm lazy, so I just do this in my head. So it's 144. Yeah, good call. So it's 10 factorial. So 10 factorial divided by 144 times parentheses 5 divided by 36 to the third times 6 divided by 36 to the second times 536. That's a 6, stupid. 36 to the second times 20 divided by 36 to the third power. I got that mess, which is something like 0.006. So, in other words, not very likely to happen, yes? It's kind of unlikely to happen. It's kind of weird. Here's a question. What would the expected value, what would it be for when you roll a dice? How many 6s would you expect to get out of 10 rolls? Okay, now that sounds binomial, because it is. If I just said what's the expected value for the 6s, it would be just this thing right here. And you'd go, well, get a calculator. I'd go 50 divided by 36. I would expect to roll 1.33 yada yada, whatever it is up there, 6s out of every 10 rolls. In other words, not very likely to happen. I'm going to get 1 6 probably out of every 10 rolls of 2 dice. That's just how these things go. Keep that in mind when you're doing this problem. When you're doing this problem and you roll the dice 10 times, it's very, very, very unlikely that you're going to get, well, it's very unlikely when you roll 2 dice. It's very unlikely you're going to get a sum of 2, yes? There's one way for that to happen. You got to get a 1 and a 1, right? Out of 36, it's a less than 3% chance of happening. It's not going to happen very often, yes? Out of 10, would you expect it to happen at all? No, because 3% of 10 is 0.3 times, yes? That's not likely to happen. Same thing with 12. You have to get a 6 and a 6, yes? There's one way for that to happen. There's about 3% chance of the time, give or take. And so you'd expect about 0.3 12s every time you roll the dice 10 times. In other words, it's not very likely to happen. It's not very likely to roll a 6 either, even though it is the most likely one to happen. 6s and 7s and 8s. 7's the most likely to happen. But it's not very much more likely. Okay? Again, that's just something I like to think about there. Okay? Multinomials and binomials. On the exam, you'll just be given a scenario. Binomial, Poisson, negative binomial, whatever it happens to be, you're going to have to read it and understand what's going on. When I read the problem right off the bat, the first thing I always ask myself is, am I playing a set number of times, yes or no? That's the first thing I look for. If I'm playing a set number of times, it could be right off the bat, so far what you know is binomial or multinomial. The second thing I look for is this. Do the probabilities remain constant? Okay? In other words, is it a situation where you're taking candy out of the back of a semi-truck? Well, if you get a semi-load of M&Ms, does it matter if you put them back in or not? How many M&Ms are in the back of a semi-trailer? A lot. So if you take 15 or 20 of them out, do you really change the probability of getting an orange or whatever? No. It's about the same, right? Because there's like, I don't know, 1 million M&Ms in there, and you grab 20 out. Really not going to affect anything, yes? If it's a little candy dish, that obviously affects things. I pulled this out, I ate it, now I go back for another one. Have I changed the probability? Yeah, then it's not binomial, is it? Okay, it cannot be binomial in that case, because I've changed the probability. Dead giveaway that it's a multinomial. The paragraph is this long, okay? The question is this long, and there's 87 numbers mentioned in it. That is a dead giveaway that you're almost 100% certain you're doing a multinomial on that problem. Because you cannot write it any other way. There's going to be a lot of numbers on a multinomial. Duh, it's a multinomial. Okay? And it's going to be this long and ridiculous problem, and the probability that I get this many of this, this many of this, this many of this, this many of this, oh, for crying out loud, it's going to be multinomial. Almost without exception. Okay? Those are the easiest ways to keep track of those two guys right there. Question? What?
I do.
Hit me.
Just to make sure I get this right. So, say like that same candy jar and whatnot, you're going to pick one out, but you put it back. Would that be binomial? If you're just looking for one specifically, would that be binomial?
So we're looking for blue M&Ms.
Mm-hmm.
Close my eyes. Pull out of a small candy dish. Oh, cool, it's blue. Throw it back in. Pull out another one. Is each trial independent of the previous one? Yes, because I put it back in, yes?
But now,
had I eaten it, that's a different story.
That's when it becomes multinomial, right?
No, because if I eat it, the probability has changed, yes? And so that's a good question. These two have what in common? The probabilities remain constant or they're independent, in either way you want to say that, okay? So if you hear independence, it could be multinomial, it could be binomial. They have that in common. Right after the break, we're going to do the one where, wait, what if I eat the candy and then reach in and grab another one? That's not independent. That has a special distribution as well. Why do these distributions exist? Because of these situations. How many times in the real world is there a live or die, win or lose scenario? All the time. So binomial is huge. How many times is there situations where you have a multitude of possible outcomes? All the time. Hence, multinomial is the thing. How many times is there where the first one affects the next one affects all the time? Each one of these scenarios happens all the time. That is why these other distributions have been developed to describe them. That's the whole point of math, is to describe something that happens in our daily world. Okay? So every single one of these, I can draw you a picture that here's an example of this, here's an example of this, here's an example of this. And that's why I like them so much, because it's just bam, okay, yeah, we've all gone outside and shot baskets. Some people are like, I didn't shoot baskets, but I told my mom I was going to roll the dice, the D20, 15 more times before I came in. And what's probably I got 5 sevens. I don't know, but that's really no different than shooting baskets, right? It's really, the idea is the same. They're probably getting a 7 on a D15 or whatever I said. I forget what I said. is not going to change each time. There's one 7 side on this 15-sided dice. That's not going to change. What the first dice got has no impact on the second dice. And why you care to be rolling the dice 15 times is neither here nor there. It's not really, in my mind, it's a little weirder than shooting baskets, but you do you. Just randomly throwing dice just for fun seems weird. At least shooting baskets, you're getting some workout. This isn't really much of a workout, but you do you, okay? But there it is. It's the exact same procedure. We've all done something like this, yes? I'm going to throw the dart 15 more times. Darts, for you might be a good dart player. You're like 90% bullseyes. Well, good for you. But still, you hit the bullseye or you didn't hit the bullseye, right? It's still a binomial situation. Okay? Got it? Cool. Take a break. Then we'll get back to it. I'm excited. I'm going to pause this thing. Play. Unfreeze. Nice. So, suppose you had a small dish of candy. Okay? And so let's just say they're M&Ms. And these ones are black, I guess. We should get a different color, I guess. Cool. There we go. Beautiful. All right, so here we go. I'm going to reach in and I'm going to select 7. No, not 7. That's too many. 5 M&Ms. Scoop them up. Just scoop them up a handful at a time. There we go. All right. So if I do that, okay, what is the probability that in my hand I will get 2 green, 2 red, 1 black? First of all, does that seem very likely to you just looking at it? Does not seem likely to me at all. There's hardly any reds. I'm taking 2 of them. Okay. There's a ton of blacks. I'm only getting 1 of them, and I'm getting 2 green. Maybe that seems reasonable. But it feels a little weird. Okay. Knowing that going in, I feel fairly comfortable saying this seems odd to me. Now, when I select all 5 marbles at one time, I reach in and grab a handful of them. Okay? There they are. Now, that's the same thing as if I had just taken 1 out, set off to the side, taken another 1 out, set off to the side, take another 1 out, set off to the side. It's exactly the same. The idea here is that it's a dependent situation, yes? Therefore, it cannot be binomial or multinomial. It is its kissing cousin, which is what is referred to as the, come on, Jay. It's on the tip of your tongue. Say it. This problem was on the test. This problem was on the test, but you didn't know the name of the distribution. This is what is called a hypergeometric. And anytime you see dependence, it's going to be a hypergeometric situation. Of the ones that we're studying, of the discrete distributions that we study. If you hear, when the question is read, if you hear dependence, not independence, but dependence, it's going to be hypergeometric. It's really easy to do. We already know how to do this problem because we did it before. We just didn't know a name for it yet. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 21, I think, marbles. And we are choosing 5 of them, right? And there's 4 blues. We're choosing none of those. There's 4 reds. We're choosing 2 of those. 1, 2, 3, 4, 5, 6, 7 greens. And we're choosing none of them. Or no, 2 of them. I'm sorry. 2 of them. And 7 black. And we're choosing 1 of them. 14, 18, 22. I don't add too good, I guess. Okay? So the numbers on top on the left better add to numbers on the left on the bottom. Numbers on the right on top better sum to the numbers on the right on the bottom. And is that what I did right? Oh, what's wrong? 7 choose what? 7 choose 1. 7 greens. 4. Oh, what did I do wrong? Oh, no, there it is, 4 choose 0. There it is. I knew there was one of them I didn't choose. What is 4 choose 0? How many ways can you choose 0 out of 4? 1. So 4 choose 0 is 1. This one here is obviously 7, right? 4 choose 2, I know it's 6, but if you don't, punch it in your calculator. 7 choose 2 should be 7 times 6 is 42, divided by 2 is 21, it should be. Okay? That said, there it is, and then you can punch it out and see what you get. So equals, what did I have? I forget now. Is it 6 times 7? Yep, 6 times 7 times 21. Divided by bin 22, 5. Right? And that comes out to be about 3%. Okay? Again, not terribly likely to happen, but we're not shocked by this. If you need to do all the combinations, go ahead and do all the combinations, yes? But if I could do them in my head, it saves me time, so less farting around. So anything choose 0 is 1. Anything choose 1 is itself. That just makes your life easier to fool with, yes? And then, of course, if you need to, if you don't know that 4 choose 2 is 6, punch it out. There you go. Okay. Just it saves me time if I don't have to type them all in. Okay. But it doesn't hurt anything either. There is no hypergeometric distribution function in a calculator. Think about how hard that would be to program, because there is no true end to how many different colors of M&Ms can be in a pot. Yes. So you'd have to have this open-ended deal. If you're making a little calculator for it, you'd have to have like kind number 1, kind number 2, and so on and so on. And you have to have like this unending supply that will be a giant pain in the butt. That's why they don't do it. Okay. There it is. Pretty easy. Notice that this guy could take on both a binomial or a multinomial. Look, for instance, same question. Maybe. Has anybody ever heard of using rubbing alcohol on these screens to make them better? I don't know. Someone told me that the other day. I haven't tried yet. Let's probably get 3 greens. Now remember, I selected 5 M&Ms at one time, yes? What's the probability that I get 3 greens? Well, this problem is all of a sudden, it's still hypergeometric because I have a small candy dish, yes? I'm taking several at a time. But this time it looks like it's binomial, doesn't it? Because either they are green or they're not green, yes? And so in my mind, when I do this problem, there's still 22 choose 5 in the basement. But how many greens are there? 7 greens. And I'm 7 greens, I'm choosing 3 of them. The other marbles, there are 15 other marbles, yes? And I must be choosing 2 of those because I wanted 5 total marbles, yes? So the hypergeometric can look both multinomial-ish and binomial-ish at the same time, depending on what the question is stated, yes? So I could be just talking about just blue marbles or green marbles or whatever, or I could be talking about I want some blues and some greens and some yellows and whatever else. It can mimic both the binomial or the multinomial, but the difference here is this. It's a small candy dish, and I'm taking them without replacement, so that's dependent. That's the key. When you read this problem, that's the first thing your eye should catch is this thing dependent or independent? If it's dependent, it's not binomial, and it's not multinomial. Okay? Those are the first things that should cross a person's mind. It's very clear that it is closely related. It's very closely related to the binomial. It's also closely related to the multinomial, but they're different about the dependency aspect. Okay. For the hypergeometric, in the case of in the binomial case, okay, so in a binomial case, that is, I want green or not green. All right, the expected value is this. the expected value is n times k over big N, and the sigma squared, the variance, is big N minus n over n minus 1 times n times k over n times 1 minus k over n. I write that to show you how ridiculous that problem looks, because it does look kind of ridiculous. No one's going to ask you to do this one. This is one of those ones where, hey, Trivial Pursuit question, what happens here? The game is this. Excuse me. So, when we do these problems, hypergeometric says this. There are k, so there's several things. Obviously, n is the total number of items in the dish. Okay? I always have to remember to ask myself. I always have to remember how they do it here. Yes, good, good, good. Yes, here we go. And k is the number of successes. Number of successes. And little n is, little n is, I forget what little n is. Where do they put it there? Little n is, oh boy, they always do it weird. Little n, oh yes, here it goes. So good. The total number of samples of size n chosen from these guys is that. So, possible ways to do that. Come on. You can do this, Jay. You can do it. Come on. Here we go. So, okay, find components, select. Oh yeah. So n is the number that you select. So in the case of the one we just did a minute ago, there were 22 marbles. That was big N. 5 is the number that we chose. That's little n. We were interested in k equals 3 green marbles a minute ago, yes? That's the one I asked about a minute ago. Oh, it was. I'm just...
Is n number of trials?
N is the number that you select. So I reached into the dish and I selected 5 marbles, right? There was 22 total marbles in the dish. That's big N. I selected 5 of them. Make sense? Mm-hmm. You could think of it as trials, but in this situation, it's better to think of it as taking them out all at the same time, in my mind.
Yeah.
Okay. Okay? So when you do this problem, the expected value of this would be this. It would simply be 3 times 5 over 22. Okay? This would be the expected number of greens out of a sample of 5, right? So what this is saying to us is the expected number of green M&Ms when you select 5 M&Ms. So that'd be 15 out of 22, which is roughly 40, no it's not. 3 goes into that 5 times 5/7 would be about 7, it's about 70%. So in other words, you expect to get about 0.7 green M&Ms out of every 5 that you choose, yes? That's what this is saying to me. Does that shock me? Well, no, I'm only taking 5 total M&Ms. So and even though green is the most likely one to show up, I'm not even going to expect to get a full green M&M when I take 5 M&Ms out of this particular jar. Okay? This is a weird problem. It's not a hard problem. It's just kind of a weird problem. The variance, you can see what the formula is, but look what it's going to be. It's going to be 22 minus 5. 22 minus 5 over 21 times 5 times k is 3 over big N, which is 22 again, times 1 minus 3 over 22. And whatever that comes out to be, that is the variance of the number of green M&Ms that you would expect to draw out of 5. Okay? Again, what does that mean to me? You know, it doesn't really mean much to me. So this is why I don't really go off on that. I like to show you that it's there, people have it. All of these distributions will have an expected value and a variance. But for the most part, we don't mess with it a bunch. Okay? We deal with binomials a ton, we'll deal with Poisson a ton. Those are the biggies. Those are the ones we do a lot of. Geometrics, we'll do it to some degree because that really matters. This one here, it's not something that we mess with a ton. We could find a probability, and we could talk about the expected value, but the variance of this one is, it's not something we deal with a ton. What does that come out to be? Do you have it? I think what you can do is 17 over 21 times 15 over 22 times, this is going to be 19 over 22. Cool. That's just gross. Cancel, 5, 7. Yeah, there's not much you can do to make that prettier. That's just gross. I don't care how you slice that. So 17 times 5 times 19 divided by 7. Oops, wait. Divided by 7 times 22 squared. So about 0.225. That would be my variance. And again, what does that mean? That doesn't really mean much to me, to be honest with you, in this case, because I don't know that I care what the variance of the number of green M&Ms I take out of a sample of 22 dishes. That doesn't mean much to me. Yeah, I know what variance means, but what does it mean in this particular instance? It means you wasted your time finding a number that, quite honestly, doesn't matter to me that much. Okay? I think it's kind of a nice, interesting deal. It's kind of neat to know that you can do it. Negative, but that's a very easy problem, so I don't want to spend a ton of time on it. Okay? Again, you've done this problem. Not this one. You've done this problem. Wait, where'd it go? You've done this problem last chapter. Where did it go? It disappeared. Oh, here it is. You've done this problem last chapter, so doing the problem is not hard. The problem is just knowing that it's called hypergeometric that's what you want to know. Okay? There's two more tonight, and again, they're closely related. There's the geometric and the negative binomial. Okay? In both cases, these are related to the binomial in that every time I play, they are independent of the previous time. Okay? The difference is, instead of playing a set number of times, I'm going to keep playing until I win a certain number of times. Okay? So in both cases, they are independent. There are two outcomes. That is how they are definitely related to the binomial. They are both independent, and they both have they are both binomial in terms of their outcomes. It's this one or it's this one. The difference is this. You're going to play until you win a certain number of times. In other words, you're not going to say ahead of time, I'm going to play 20 times. You're going to keep shooting baskets until you make 5. You're going to keep rolling the dice until you get 6 ones. You're going to keep having kids until you get 3 girls. Okay, whatever it is. You're going to keep playing until something happens. Binomial says I'm going to play 5 times and then I'm stopping, period. That's the difference between these two guys. Okay? So again, very similar to binomial because they're independent and they have two outcomes, but they differ in that you're going to play until you win a certain number of times. So the difference between these two is this. Geometric, you play until you win once. This one you're going to play until you win X times. Now, if you're smart, you realize that the geometric is a special case of this guy, yes? That guy is a special case of this guy. Okay? That over there is when x is equal to 1, yes? So if x equals 1, they're the same. So this is, I'm going to play until I win 5 times, then it's negative binomial. If I'm playing until I win 1 time, technically it's geometric. It's also negative binomial, yes? It's like saying that, oh hell, I feel like I can't even use that example anymore. But I feel like if you knew that your grandpa was a grandpa, you're certain he's a dad too, yes? It's the idea that a rectangle is a square is a rectangle. That's not true the other way around, yes? So that is that geometric is a negative binomial. It's a special case of the negative binomial, okay? Now, that said, I prefer to do it this way. I like to start off with geometric. You're going to shoot a basket until you make 4. Until you make 1. Shoot basket until you make 1. Okay? And you are 40% from the foul line. There you go. What is the probability that it takes that your first make, I should say this, your first basket happens on 5th shot? Okay? Well, if I'm still shooting on the 5th shot, what have I done the first 4 times? I've missed, yes? So I had to go 0.6 times 0.6 times 0.6 times 0.6 times 0.4, right? Because I had to miss, and then on the 5th time I made it, yes? The easiest way to write that problem is to say this. It is 0.6 to the 4 times 0.4, yes? Or if you prefer, and I do, Derek, I prefer, that is to say it's q to the x minus 1 times p. Okay? So I wanted to shoot 5, I wanted to make my first shot on the 5th trial, yes? So I had the first 4 shots were misses, and then I made one on the 5th trial. Can I switch the orders of these around? No, because if I switch the orders, in other words, it has to go miss, and then make. Because if I had made a make right here, what would I have done? I would have quit shooting at that point, yes? Because I said I'm going to play until I get 1 make. Well, if it happened right here, you would have gone home already. You'd have quit. So if I'm still shooting after the 4th time, I had to have 4 misses in a row. Because that's what I said. I'm going to keep shooting until I make 1. So as soon as I make 1, I'm done. Therefore, there's no choose anything out front, yes? In other words, I'm not going to mix them, match them around. It has to go miss, then make. Because that's what I said. I'm going to play until I get 1, and then I'm going to stop. Okay? Now, negative binomial is almost the same, except, watch this. If I change this problem, you're going to keep having kids until you get 3 girls. Wow. You're just going to keep having kids till I get 3 girls. We're just going to keep playing until we get 3 girls. But it's number 20 already. No, we said back in the day we're going to keep going until we have 3 girls. Are you sure? Yes, that's ridiculous. But let's just pretend. What is the probability that the 3rd girl happens or shows up on the 11th kid? Okay? And so if you're still having children after 10, how many girls, but you could stop on 11, that means you've played the game 10 times so far, yes? And you've got 2 girls, yes? Because the only way I'm going to quit on 11 is if I already have 2 girls, and then I get a win, a girl on the 3rd time, on the 13th, or whatever they said, the 11th time. Now, what that means is this, is that you get boy, girl, boy, whatever. There's 10 children, 2 of them are boys, yes? Or 2 of them are girls, yes? How many ways can that happen? It can happen this number of ways. 10, choose 2, right? So 0.5 to the 2 times 0.5 to the 8. This is for your first 10 kids. Okay? So far, out of this 10 kids, I've got 2 boys, or 2 girls and 8 boys, yes? In any number of orders. Could have had 2 girls right off the bat and then 8 boys in a row. It doesn't matter. This is the number of ways it can happen. And then what has to happen on the 11th kid? What do I have to get? Another girl. This is your 11th kid, which of course is a girl. Okay? That is how you do negative binomial. Now, Excel can do this problem by hand. Excel can do this problem using a computer. Okay, and that's great. Your other calculators cannot do it. But when you do this problem, look what I do. This is what I do right here. This part right here, if I'm using anything except Excel, I'm going to do this. I'm going to do, it's a binomial dist, or binomial PDF, I mean. It's a binomial PDF I've played 10 times. 0.5 is the probability of success, and 2 girls so far. And then whatever I get for an answer, I'm going to times it by 0.5. That's how I would do it on a TI-89 or a TI-83. Okay? To me, that's the easiest way to go. Because up to this point, it was a binomial distribution. I've had 2 girls, the rest boys, whatever. Now, if I'm going to quit on the next one, I know I had 2 girls already. So if I'm going to quit on the next one, it has to be another girl. So there it is. Now, that's why I like Excel. Excel has this distribution in it, which I think is kind of handy. It is just equals negative binomial dist. Give it to me. There it is. So it wants the number of failures first. Well, failures in this case would be boys, yes? So out of 11 kids, how many boys did we end up with? We wanted 3 girls, so the other 8 kids must be failures, yes? Boys, so 8, comma. Number of successes was 3 for 3 girls, right? Probability of success, 0.5. And then comma 0, just like always. Okay? Because I don't want a CDF, I want a PDF. And if you do this, you will get this, about 2% chance that happens. Now, does that mean that's a 2% chance of having 3 girls out of 11 kids? No. It's the probability that your 3rd girl happens on the 11th kid exactly. Okay, that's a different thing. Okay, because if I wanted the probability of 3 girls out of 11 kids, it'd be this problem right here. So if I want 3 wins out of 11, 0.5, comma 0, that 8% right there is probably I get 3 girls out of 8 kids, out of 11 kids, I mean. That's not what the question asked. Probably the question asked was probability that your 3rd girl happens on the 11th kid. Okay? That's what it asked for. So that's how you do these problems, and it's kind of an easy deal. Same deal here. So you're going to keep asking. Ooh, here's a. Oh, I can't do that one. That was on the test.
That's fine.
No, I can't use that one. By the way, on the test there will be some crazy problems that are similar to one of these guys. Some of them you might find to be, well, it could be that, I guess, maybe, sort of. It's a little different than that. It's kind of like that. It might be. I don't know. I do that on purpose. It's going to be somewhat open-ended, somewhat ambiguous on some of those questions. That's one of your things. But here's one. A classic one was always back in the day. My dad. Oh, that's not. I don't want to do that one because that's on the test too. Okay. Yeah, okay, let's roll some dice, I guess. Well, yeah, okay, let's do it. So, yeah. So we're going to roll a 10-sided dice. Until it lands on a multiple of 5 3 times. Well, multiples of 5 are 5 and 10, yes? On a dice? On this 10-sided dice? Presumably, yes? So there's a 2 out of 10 chance of that happening. This is my probability of success. Is each time I roll the dice independent of the previous one? Yes. Right? So the first roll doesn't affect the second roll at all. Number 2, am I playing a set number of times? No, I'm going to play until something happens. Okay, so it can't be binomial. Because if it's binomial, then I'm going to roll the dice 15 times or something. Okay? So it's not that. It has to be negative binomial. So listen, I'm going to roll until I land on this. So the question is this: what's the probability that the third multiple of 5 happens on the 15th roll? Okay? Well, listen, if I could possibly quit on the 15th roll, that means through the 14 previous rolls, how many have I gotten? 2. So it's going to be something like this. If you're doing it by hand, it'd be 14, choose 2, right? Because the first 14 times I rolled the dice, I've gotten 2 multiples of 5 so far, yes? I know that because if I'm going to be able to quit on the 15th roll, I had to have 2 already, yes? And then, so I'm going to have 0.2 to the 2 power, 0.8 to the 12 power. So this is for your first 14 rolls. And then I'm going to have to get another win on the 15th roll, yes? Okay. If you're doing this by hand, or well, quote unquote by hand with a calculator, okay, you could do it the old school here. So I could do combinations 14, 2 times 0.2 to the 2 times 0.8 to the 12 times 0.2 again. About a 5% chance of that happening. Or, if you like it better, and I do, equals negative binomial. And number of failures is 12. Number of successes is 3. Probability of success is 0.2, comma 0. It's 5%. Exact same probability. Okay, whatever works for you works for me. Okay? I like negative binomial because there's not a whole lot to the thing. Okay? Notice just for grins, if you were flipping a coin, no, not flipping a coin. Why could flipping a coin not be 1? Could it be 1? Could it be? Could flipping a coin be geometric or negative binomial? Yes, I could flip a coin until I get ahead, yes? It has to be independent. So flipping a coin fits the bill, yes? So I could flip a coin until I get ahead. What's the probability that the first head is on the 6th flip? I don't know. But so far I've had 5 flips. How many heads have showed up at this point? None. Times 0.5 to the 0 times 0.5 to the 5, yes? This is your first 5 flips, yes? And then I get another 0.5, that's for the win, yes? You're like, wait, but what is 5 choose 0? 1. This is also 1, yes? So this becomes q to the 5th power, yes? Right? Because I lost 5 times and then I won. So what I'm trying to say is that the negative binomial and the geometric will always work out to be the same. Now you can do this in Excel as well. I just think you look silly using Excel for this. This is a very high-powered function for no more than you're doing here. So negative binomial, how many failures did you have? 5, right? Because we're playing until we get, and it's going to happen on the 6th roll, yes? So I had 5 failures and 1 success, and then 0.5, and then 0. And what did I say it was? Oh, I didn't think I figured it out, did I? Equals 0.5 to the 6th power. Hey, it's the same, right? It's the same. Okay? there's a 1.5% chance of that happening. It's not very likely. By the way, same percentage chance that, no, this is twice as big a percentage as Richard wanted me to go on the card problem earlier, by the way. Right? Same exact thing, yes? In other words, if it was truly 50-50, the probability that I would have gotten 5 blacks in a row and then a red, if that was true, would be 1.5% chance of that happening. Okay? You know, obviously it didn't because my numbers were different because our assumption was poor. Okay? Now, negative binomial and geometric. Big deal is this. It sounds binomial-ish until you realize we're not going to play a set number of times. That's the big key difference between these guys. Binomial says I'm going to play this many times and then period, I'm done. Geometric, negative binomial, those two say I'm going to play until I win a certain number of times. There's a big difference, okay? So that's the big key there. They sound a lot alike because they are closely related to one another. The difference is binomial is a solid set n. That's not true for negative binomial or for geometric. Okay? Think about this. Are there things in life where you stop at the first one you get to? It'd be creepy, but picture this. You're going out at, hey, will you marry me? Will you marry me? Will you marry me? You're probably going to stop at the first one that says yes. I'm guessing. That seems weird otherwise. Is that the same? No, I don't think everybody has the exact same probability of saying yes to you. That's weird. So you understand there is this idea that it sounds like that, but in real life that situation probably isn't exactly negative or geometric because not everybody has the exact same probability of saying yes to you, right? When you go and ask them such a weird question.
So that kind of thing, you would just take the average probability, right?
Maybe. But here's the deal too. I would say more that's creepy. No, you're not going to go ask some random person, are you?
Yeah, but for that kind of thing.
But what I would say is this, of the people who you would probably bother to go talk to and ask them, let's say out, they probably all have basically the same percent chance of saying yes to you at that point. The same percentage. You're probably not going to go ask people who don't know you, hey, random stranger, you're going to go dance with me? That's weird. Of the people that you know and associate with, they probably all have more or less the same probability of, and then, yeah, probably average it. The question would be, where would you go with numbers for that? And I don't know. I don't know. If you're a person who randomly asks girls out all the time, you might have a pretty good idea what your shot is. Other people, like, oh, here's a classic example. Derek says, I'm shy, I don't want to ask this girl, oh my, and the girl is like, I wish he'd just freaking asked me already. And Derek's like, oh, I don't know if she'll say yes. And of course, everybody knows she's going to say yes. So in that situation, you know, in that case, it's pretty clear that you're probably only going to target the one situation, and you know, he goes in. In that situation, he probably underestimates what his odds are. He thinks he's going to strike it. Well, even it's a sure bet she's going to say yes. All you have to do is get off your butt and ask her, for God's sake. In that situation, again, so in the real situations like this, we have to do a little bit of assumptions, okay? And then, of course, this is where psychology kind of plays into this, which kind of grosses me out at that point, because that's where people mess up my numbers, all right? With good data, you know, we're on an assembly line, for, you know, making zillions of product all the time. The data is about the same coming off all day long. I'm making crackers or you know, cookies or wherever we're producing. It doesn't change a whole lot unless the machine breaks or something, right? And when that happens, I'm going to catch it pretty quickly, right? All of a sudden, I'm making giant Ritz crackers that are this big, this is unfortunate, or you know, whatever it happens to be, you know. But a guy I know, I taught his kids. He works at Widmer Brothers in downtown Portland. He's one of the head brewmasters, and they all day long they test the beer and they see how it is and what's going on with it and whatnot. You know, if that gets out of tolerance just a little bit, man, they flush that crap down the toilet because you cannot sell garbage beer. It's a good way to lose customer base, right? You want it to be the same quality all the time. But when you start putting people into it, it gets all messy because people have too much variation. People are weird, okay? It's hard to do that with people. That's not true for one person. If you have one person that you're dealing with constantly all the time, let's say your girlfriend, you have a pretty good idea how she's going to react in a certain situation after you've been with her for any length of time. You're like, well, then that's not to say you're not surprised completely from time to time. But it's a pretty good bet when this happens or that happens, you're like, oh crap. you said, oh crap, because you've been here before, you realize that this or this is gonna happen afterwards, and you feel pretty confident that's a true story. Because it's one person, it's not like you're talking about people in general all over the map, but that's when it gets messy. So, there's that. So this week, I covered everything I was gonna cover this week, including in the video, okay? I will probably throw a few videos up if you want to reference for, you want to get some more information in negative binomials or whatever. Okay, next week we're going to look at Poisson distribution, which is the only one that I didn't talk about. It's the last discrete one that we're going to talk about. It too is related to binomial. They all have this relationship with binomial. Even multinomial is related to binomial. Yes, they all have a relationship there. And so I'll post some more videos so that you can watch if you want some more practice. I think I will wait till next Wednesday to post the assignment because I want you to have seen Poisson beforehand. I want you to start through it and go, oh, I think that's binomial. Well, it's probably Poisson maybe. I want you to feel comfortable when you're doing these guys. Okay? Yes, sir.
Do you already have information about the project?
No, that will be coming out. What week is this? Week 6, yes?
Yeah.
Is it 6?
Seven.
Is it 7?
Really?
Nuh-uh.
Yeah.
For realsies?
They turn for week 6, which makes us week 7, but I think that would be
I would think it was 5 to 11.
God, I hope Isaac's right. Whatever. Yeah, I will be putting that out. It's
Hey, you
not a
don't have to
very.
assign one to it.
No, there will be. It's not a very hard one. So a few hours worth of work, and that's so don't like. It's not a huge project. Yeah. So. Did I talk about next week in class? Maybe I talk about next week in class. Maybe I put a video up. I haven't decided. We'll figure it out. Alright. So, yeah, I think I'm done talking. I think you'll find the ones on this assignment. Maybe I will put the assignment out. I might just say hold off on some of them. I don't know. I'll send you an email if I change my mind. Okay. The ones in the book, you do them. You're like, oh, I feel comfortable with these guys. Good. That's learning them. Obviously, if you're in the binomial section, you better be using binomial. The ones on the homework assignment, on the page I hand out to you, the assignment, they're all mixed together. And that's the trick for that one, is understanding which one's which. Okay? The math is very straightforward. It's the understanding which tool to use. Okay? Question? You're looking to give a question? No? All right. Run along. Have a nice day. If you want to see the answer key, come poke at it up here. Or argue. Wait, here it comes. Oh, I think you messed up on this one, Jay. Thanks, Isaac. That's great. What did I mess up, buddy?